All right, welcome back, everyone. I'm Wojciech Jaros from Dartmouth College, and we have two exciting papers in this natural appearance session. As a quick reminder, if you're a registered attendee, make sure to log into Rocket Chat. You can post your questions there even as the papers are being presented. So unlike in a physical conference, it's not rude to start a discussion, and then I'll look through that at the end of the talk and ask your questions. Just go to EGSR2020.London. It has all the links you need there. For the people that are on YouTube, the organizers and myself will do our best to try to look at the comments there, and we'll also try to incorporate them to the best of our ability. Okay, so with that, let's dive right in. The first paper is by Sebastien Hillaire from Epic Games, and we'll play the presentation now.
Hello everyone, I am Sebastien Hillaire and I'm going to present to you the scalable and production-ready sky and atmosphere rendering technique we use in Unreal Engine. So what are we talking about? The sky is the result of complex light scattering on particles within the atmosphere. On Earth, the sky has a rich blue color during the day and features a beautiful mix of blue and green color at the horizon. While during sunset, more complex yellow, green and red tones are visible, as you can see on the bottom image here. When it is happening between object and your eyes, this physical simulation is called aerial perspective. Those objects then look like they are in fog. Last but not least, clouds are also part of the atmosphere, but in this presentation we will ignore them. So many different types of atmosphere exist aside from the well-known Earth atmosphere. For example, on Mars, the atmosphere has a different composition resulting in a reddish color at daytime and a blue sunset. Titan's atmosphere is even crazier. It features several layers having different composition, resulting in an even more color variations. So the light will scatter several times within the atmosphere before reaching your eyes. This is important effect to simulate to achieve rich atmosphere visual. We cannot take real-world captures with and without this phenomenon, unfortunately, so here are some artificial examples achieved using path tracing. At the top, you can see that on Earth, during sunset, multiple scattering is a critical part to achieve believable results and avoid a yellowish atmosphere look. At the bottom, images shows that multiple scattering is important for the light to fill up the space between the camera and, for example, landscape, when you are inside a volumetric shadow. And in this case, this is a result of light scattering around the mountains before reaching your eyes. So several methods have been proposed to render atmospheres. Nishita and O'Neill proposed a rematching method. However, they were not taking into account multiple scattering and there was no solution provided to apply the aerial perspective on translucent objects. Another possibility is to fit a mathematical model on the sky color itself, actually learning how it should look according to some parameters. However, those models are limited to views from the ground and also to the range of possibilities that the model has been fitted to. A more complete approach to sky rendering are the lookup table-based model. The most popular one being the model from Brunton, storing light interaction into a four-dimensional LUT. It has been applied successfully in many games with a few simplifications. However, it does have some limitations. Some visual artifacts can be seen at the horizon in some cases, and it becomes unavoidable when the atmosphere is made thicker than the Earth, for example. The high-dimensional LUT is expensive to update and requires time slicing to remain in budget. And in turn, this adds latency. Multiple scattering is an iterative process. It requires n iteration to be computed to compute the results of n order of scattering. And last but not the least, it can support hard shadow from opaque, but not really soft shadow from clouds, for instance. So what is it we wanted? We wanted artistic freedom and to be sure that the tech is usable in editor. We wanted a high visual quality without any artifacts. We wanted to be close to the ground truth in the way we present the atmosphere and handle multiple scattering. And we also wanted the result to be available instantly to avoid latency. We wanted the technique to be scalable. Our games run on mobile, and we also wanted the atmosphere rendering performance to be decoupled from the screen resolution. For example, when you think about creative 4K. And also we wanted to support views from space, because why not? This is interesting. So this is the result we got in Unreal Engine before we dive into the details. So you can see the first video shows the atmosphere being rendered in real time in the editor. The sky is updated each frame, and the atmosphere can be tweaked in real time to match, for example, the Mars visuals instead of the Earth. You also have a second video showing a view from space of planet Earth with a sunset. And the last video showed that one can fly from ground to space seamlessly and even represent tiny planets with soft volumetric shadows from clouds. So to get there, we started by looking at what really is required to render the sky. One can easily notice that the distant sky is of very low frequency. Even the mist-scattering blob around the sun the blob around the sun is really looking like a blob. It's smooth, and the aerial perspective itself is also very smooth on screen and in depth. The only high frequencies that one can see are the rapid change of atmosphere color near the horizon and the variation due to volumetric shadows. So from this simple analysis, we propose a way to render all those low-frequency visual components into low-resolution lookup tables. This will automatically decouple our atmosphere rendering technique performance from the screen resolution. And we also recognize that the multiple scattering is important, so we propose a new way to store and evaluate the multiple scattering in the lookup tables. And all this will make our technique scalable from mobile to high-end PCs. So in this work, we represent the atmosphere the same way as it has been done previously. We simulate radius scattering, mist scattering, ozone absorption, and more. Please refer to the paper for more details. So about our rendering technique. How do we render the atmosphere? We will use the typical volumetric remarching with sample count adjusted based on distance. For each sample, we evaluate the light transmitted through the atmosphere, phase function, the atmosphere material, and this way we can deduce the amount of light scattered toward the camera and the transmittance over the background, for example, over the mountains. Multiples and so on. We continue and we do that until the end. Multiple scattering usually is typically too expensive to evaluate using remarching because you need to integrate over the hemisphere several samples and recursively. So it will be achieved using the new technique, the new multiple scattering LUT we propose, and we will describe that later. So as mentioned previously, we sometimes need to evaluate the light transmitted through the atmosphere to a point. And instead of remarching, we use the same two-dimensional LUT as proposed by Brunton before, parameterized from the point altitude and the light direction. The sky view LUT is the lookup table we propose to render the distant sky. It stores the remarching result using a lat-long mapping. It can store the contribution of multiple suns. And please do note that the latitude mapping is not linear. So this is done in order to maintain the amount of details at the horizon. As you can see here, if you use a linear mapping, you will see a linear interpolation artifact being visible. So using this LUT, you can now render the distant sky, as you can see here. And the sun is composited separately. So the aerial perspective luminance and transmittance is evaluated and stored in a volume texture, mapped onto the camera frustum, as proposed in some previous work. This can then be applied on opaque and translucent surfaces. So this is without anything. This is with the sky view LUT applied. And this is with the aerial perspective LUT applied on the meshes. So now, how do we evaluate multiple scattering? We already mentioned we would like to move away from high-dimensional tables and iterative process from the Brunton approach. The LUT should be cheap to compute, so path tracing is out of question. We said we wanted a LUT that can be sampled while remarching the atmosphere. So it should be cheap to generate and based on physically based parameters of the atmosphere. So we are going to make some approximations. It has been reported that light scattering within a medium will quickly result in an isotropic like scattering behavior. We make the approximation that all scattering phase functions are isotropic starting from order 2 then. It has also been reported that higher scattering orders can be deduced from the second scattering order. And that is what we will leverage here. So we need to evaluate the isotropic second order scattering for each point, altitude, and sun zenith angle. We do this by integrating the scattered light around each point within the atmosphere along 64 directions. But during this phase, we consider the light illuminance to be a unitless value of 1 in order to have a second order transfer function of unit 1 over steradiant. This is important for later. In order to compute the higher scattering order contribution from the second order, we will use a similar approach to Zinke method called dual scattering for hair rendering. We will assume that the participating media is smooth in the neighborhood of a position and that the second scattering order reaching a point is the same as the one reaching other points in the neighborhood. Also, we will assume that multiple scattering is never occluded by mountain and such. This should have a low visual impact because usually light can scatter around objects. So if we assume the second scattering order is the contribution to higher scattering order, we only need to compute a scattering gathering transfer like function from the neighborhood using a particular around a particular position. And we do this by integrating the contribution of the neighborhood around a point within the atmosphere using 64 directions again. And during this phase, we simulate the transfer of a value of 1 according to the atmosphere properties. And this results in FMS, you can see here, which is a unitless transfer function from the neighborhood toward a point. And so now for each position and sun zenith angle, we have the second order scattering transfer and a neighborhood scattering gathering transfer function. We can compute the infinite scattering contribution from FMS using an analytical property of geometric series, and this gives us FMS in caps. By multiplying it with the second order scattering transfer function, we can compute the infinite isotropic multiple scattering contribution factor we call psi here. You can see in this case how the second order, the third order, and the fourth order, and so on appears automatically. And finally, it can be combined with the actual sunlight illuminance at runtime to finally get the luminance contribution due to multiple scattering inside the atmosphere. And so we store the psi multiple scattering value into the multiple scattering LUT we propose, and this is simply parameterized from the sample altitude and sun zenith angle. And this is possible because the phase function is considered isotropic, so this LUT can stay simple. Let's have a look at some results now. We have compared our approach to the updated technique from Brunton 2017 and a simple volume path tracer we have developed specifically to be our ground truth. In the article, we report RSME comparisons, but not here. On this slide, we compare the result when rendering an Earth-like atmosphere during daytime and sunset. They all match very closely. One can notice that the Brunton model, however, does lose a bit of color saturation in the mist scattering lobe at the horizon. This is likely due to the trick used when misscattering is stored as a single float value in the scattering lot, which will be the approach used when rendering a game to be efficient. These rendered images are views from space of Earth, Mars, and a tiny planet with a thick and large atmosphere. Again, we can see that each and every model matches the ground truth and works great. One can notice, though, that Brunton models fails to represent the volumetric shadow of the tiny planet. This is the default behavior of the model. After discussing with Eric Brunton, it actually is possible to make this look good by changing an input of the scattering lot parameterization. However, the quality of the aerial perspective will then suffer when looking at it from the ground. And again, this issue can be compensated by increasing the lookup table resolution, but you have to do this. So now we compare results when the atmosphere density is made higher. This reveals the importance of taking into account higher multiple scattering orders. You can see that integrating scattering up to order 5 is not enough to faithfully represent the atmosphere even using a path tracer. Higher orders must be taken into account. In this case, up to 40 orders before the visual impact becomes negligible. You can see that our model is very close to the ground truth, thanks to the new multiple scattering and lookup table approximation. And the model from Brunton unfortunately suffer from the same artifact we described before, especially the one at the horizon, and that is emphasized by the higher atmosphere density. And it also fails to represent a higher scattering order, likely due to the numerical precision issues. So there are some caveats to be aware of when using our new multiple scattering lot. It does work nicely for isotropic me-face function, but when it is made strongly anisotropic, it will start to look different as compared to the reference. You can see here that the sun highlight and the background looks different as compared to the ground truth. And last but not the least, for very high scattering coefficients that are colored, the multi-scattering luminance hue can start drifting as compared to the ground truth, as you can see on the right here. Here you can see the performance when building those LUTs on PC and mobile. Please do note that the transmittance LUT can have a lower resolution on mobile and use less samples if you are willing to accept minor visual differences. So you can see that on PC it's very fast to render, and on our lowest spec iPhone 6s, you can see that we have roughly a 1 millisecond cost of rendering the LUT. Yes, so we mentioned space rendering and enabling volumetric shadows. In this case, in order to maximize quality, you can use the LUT when you go to space, but you will lose a bit of quality at the horizon. In this case, we suggest that you switch to per pixel tracing, sample jittering, and TAA to resolve the noise and achieve the sharpness you are after usually. So you can see here some example of cloud volumetric shadow within the atmosphere, and the camera traveling super fast in the atmosphere and going into space. If this per pixel tracing cost is prohibitive for your use case, it is of course possible to simply store the shadow as part of the sky view LUT and the aerial perspective LUT. And we have a way to do that. You will just have to play with their resolution and the sample count in order for the volumetric shadow to look good for your content, basically. So the technique has shipped in Fortnite since chapter 2, and in the Unreal Engine 5 tech demo called Lumen in the Land of Nanite. So to conclude, I have presented to you a sky and rendering technique that is efficient and proven in production. It supports dynamic atmosphere and time of day, multiple scattering, views from space and ground. It can scale down to mobile when with shippable performance. The source code is of course available from the public Unreal Engine website, as well as from my GitHub repository, where you can also find our...
All right, welcome back. Thanks for the nice talk, Sebastien. So let me just remind everyone that's watching, please join the Rocket Chat to post your questions there. If you are only on YouTube, then we'll try to incorporate your questions as best as we can. In the meantime, as people are thinking of their questions, I have a couple thoughts after watching the talk. So I was wondering, there's been a long history of trying to get more accurate sky models. And I was trying to think of other sort of prevalent, sort of homogeneous participating media that we might run into. And I was wondering if your method could be used directly or adapted, say, for rendering underwater scenes.
Yes, that's a good question. I think it can. We can try, but because in this case, like you will likely have higher absorption and scattering coefficient in this case, I think it will diverge quickly. Like I showed at some point, for a very strong scattering and absorption coefficient, it can fail. Like you just have a huge shift, so it may fail, but definitely something I want to try also. Yeah, so I definitely agree with you. Yeah.
And which part of the approximations you're taking do you think that error is coming from?
It's likely, I think the most important part in this case is because, well, you assume that the second scattering order is the same for all the points you gather from. So then I think that like will bias it. I think that's the main reason, aside from the low amount of sample we do when we are in real time, we need to do a low amount of samples. Okay. But I think that's the main reason, yeah. That's the main,
I'd be interested to see how well that works and see people extend that. So we have a question from Gurpreet Singh. He said, nice results. How do you obtain the parameters for the alien planets like Mars and Titan? Are there any online resources available for getting these kind of parameters?
Okay, so for Earth, there are some online resources, and you can recover coefficients from, and they're all spectral, so you need to recover the coefficient from there, from spectral to RGB. That's what we do. I've just used the one from Brunton. I think he has derived them, like the absorption coefficient from ozone. You can find them this way also. For Mars, I don't know, and Titan, I don't know also if they are available. Yeah. I think I looked for them at some point. I never found anything, but it would be cool to find them actually.
So you just have artists set these by hand?
Oh yeah, this one I was just tweaking the coefficient by hand. Yeah.
All right. So since there's no other questions on the chat, I have a couple others. So I'm curious. I assume you have this infinite sequence that you approximate at analytically, assuming that all the scattering orders are the same. I assume that this only converges under like energy conservation conditions. So did you run into issues where with certain parameters it would fail to converge?
Yes. So when you integrate the transfer factor from the neighborhood, in this case, usually what you do when you integrate, you first accumulate scattering and then apply transmittance, or the other way around. And then you can have a precision issue in this case, and it can explode. So the only way to counter that is to use the analytical integration. Along the way, I proposed like a few years back, and this like do like a proper analytical integration over a segment by segment. Then it should not explode. I've not seen it yet. I'm not saying it cannot happen, but I've not seen it yet.
Okay. So it seems that there's a question coming in from YouTube. So Brunington's sky LUT parameterization provides a sharper horizon, but was this not used because the space view starts to break?
For a sharper horizon. Yes, it does also provide a sharper horizon, but it starts to break also. The higher you go to space, also it can also break, I think. But yeah, the one I propose, like the sky view LUT, is probably a bit more sensitive. And that's why when you go to space, usually I think it's fine to switch to, I mean, you can still keep the LUT, and like the nonlinear parameterization, we could make it dynamic depending on your altitude. We've not done that. But the alternative we do instead is to just switch to per pixel tracing, which is usually you have the budget when you're in space and it's higher quality.
Okay, great. So I encourage everyone to keep posting questions on Rocket Chat. We can have a nice discussion during the entire conference. But for now, let's move on to the next talk. So the second paper in this session is a new method for rendering granular materials, and it's co-authored by Cheng Zhang and Shuang Zhao from UC Irvine. And we'll start the presentation now.
Hello everyone, I'm Cheng from UC Irvine. I'm here to talk about our recent work on efficient rendering and modeling of granular material. Granular material consisting of large assemblies of microscopic granules are common in our everyday life. A pile of sand contains hundreds of thousands of mineral grains. Snow is comprised of numerous ice flakes. A smooth spice is the aggregation of millions of fine powders. All these materials are characterized by fine-scale details at grain level and smooth macro-scale appearance due to multiple scatterings between grains. In the context of physics-based rendering, treating each grain as explicit geometry and simulating global light transport using path tracing is a general solution. Even though this method preserves grain-level details, it is inefficient or even impractical for large collection of grains. So far, rendering granular materials accurately and efficiently still remains an open problem in the rendering community. In our paper, we introduce a new multi-scale framework to render heterogeneous and polydispersed granular material. Different from previous work, our framework relies on a pre-computation that can be reused for grains with varying optical properties. We also proposed a tile-based representation that can be used to describe large-scale granular material with non-uniform distribution. Using our method, it is now practical to render scene containing billions of grains with complex distribution. This animation is rendered using our multi-scale rendering framework and tile-based model. The scene contains 100 billion grains, which cannot be handled using any of previous techniques. Before moving on to the details of our method, it is necessary to introduce some related previous work. As suggested in Mueller's paper, the appearance of granular material can be separated into high-order and low-order component. Low-order component contains the high-frequency visual structures, including geometric details, sudden color changes, and glints. It is caused primarily by light interacting only a few times with the grains. On the other hand, high-order components containing the smooth large-scale appearance, which is caused by light interacting multiple times with various grains and diffusing in all directions. To efficiently render granular material, different techniques have been proposed to accelerate either low-order component or high-order component. To accelerate high-order scattering, one approximates the granular material with homogeneous medium, which can be rendered using classic volumetric path tracing. The well-known diffusion approximation could be used to further accelerate the volumetric rendering. However, most method is limited to homogeneous and monodispersed granular material, where monodispersed means that all grains need to have the same size. In 2016, Mueller proposed a multi-scale modeling and rendering framework for heterogeneous and polydispersed granular media. Under his framework, technique proxy path tracing is introduced to accelerate low-order scattering. For high-order scattering, they extended Mond's volumetric approximation to handle heterogeneous mixtures of grains with various sizes. On top of the median approximation, they proposed a volumetric shear transport function for better performance. One thing to notice here is that proxy path tracing and volumetric path tracing require per-grain pre-computation, which introduces some problem. The appearance of a grain is determined by various factors, including geometric shape, interfacial BSDF, and interior volumetric properties. In the scenario of rendering a large collection of grains, it is reasonable to assume that the interior volume is homogeneous. Then, the volume parameters mainly reduces to volume density and single scattering albedo. Whenever any of these factors is changed, according to Mueller's method, it is required to redo all the pre-computation. However, it is not unusual for a real scene to contain grains of various colors or optical densities. Just like the example shown here, where the interior volume density or albedo is not identical for any two grains in the scene. In such cases, previous method suffers, as it cannot handle material with richly diverse properties. Theoretically, we need to do all the pre-computations separately for every single grain, and of course, it is not practical. Next, I will discuss how our method tackles this pre-computation problem for both proxy path tracing and volumetric path tracing. Let's begin with a recap of proxy path tracing proposed by Mueller. The key idea for proxy path tracing is a novel BSSRDF model termed as grain scattering distribution function (FG). This function describes the amount of light leaving the bonding sphere of a grain at location XO in the direction omega O when the incident light enters from Xi with coming direction omega I. With the use of GSDF, we no longer need to simulate the light transport within the grain. Instead, light transports directly between points on the bonding sphere, which in turn greatly reduces the rendering time. The final GSDF can be expressed as the sum of the light that hits the bonding sphere but meets the grain, and the light that actually hits the grain and leaves the bonding sphere at somewhere. One thing important here is that the fraction of light that hits the grain, as well as its angular spatial distribution, depends on grain's optical density and single scattering albedo. This explains why the pre-computation cannot be shared across grains with different optical property. The key idea of our method is that the light contribution can be decomposed based on the number of scatterings inside the grain. By assuming that the interior volume is homogeneous, every time the light scatters inside the grain, the light path throughput is scaled by the grain's albedo. For a fixed density, the total light contribution can be expressed as a sum of a degree k polynomials of albedo. The number k should be chosen to avoid noticeable energy loss. By pre-computing coefficients rather than the sum of the polynomial, our GSDF no longer depends on the single scattering albedo. Of course, for different grain density, the coefficients are different. To remove the dependency of the density, we can pre-compute the coefficients at a series of fixed densities. Then, given an arbitrary density, we can evaluate the coefficients using a first-order approximation. For more details, please refer to our paper. Our method can also be applied to the volumetric approximation mentioned previously, where the approximated RT parameters also depends on grain's optical density and albedo. Similar to GSDF pre-computation we just discussed, to remove such dependencies, we represent RT parameters using a polynomial of grain albedo as several fixed grain densities. Then, given any arbitrary grain density, the RT parameters can be computed using first-order approximation. The story is a little bit different for highly scattering grains. Remember that we used the degree k polynomials to formulate GSDF and RT parameters. To support highly scattering grains, the order k needs to be large to avoid noticeable energy loss. However, this leads to not only large data footprints to store all the coefficients, but also slow rendering due to expensive polynomial evaluation at runtime. Fortunately, according to our experiments, the polynomial coefficients for any GSDF or RT parameters decrease in a roughly exponential fashion when k is large. Therefore, we can approximate all the high-order polynomial coefficients using a unique exponential expression requiring only one single parameter tau. We call this new expression extended polynomial. Here we show an example to demonstrate the necessity of our extended polynomials. This castle model consists of highly scattering grains. With our extended polynomial representation for GSDF and RT parameters, the result matches the reference closely. However, by naively truncating the high-order coefficients, the improvement in performance is similar, while the result suffers from high energy loss. In addition to our multi-scale rendering framework, we also proposed a tile-based model to depict large-scale granular material with non-uniform grain properties and distribution. Here, we provide a preview of two results in the paper using our model. Both things contain billions of grains, which apparently make it impractical to store all the information for every grain explicitly. In our model, The basic building block tile is a three-dimensional cell recording the locations of a few uniformly distributed grains of same size. The key point here is our model allows the grain number and grain size to vary between tiles. For a specific thing, grain attributes including grain size, packing density distribution, volume density, and albedo can be specified using 3D grids. Every grid is comprised of a number of smaller tiles. Next, I will talk about how our model supports flexibility in grain number and size. The core of our tile-based model is a template tile, which stores a fixed number of highly packed spheres without any overlapping. To support various grain size and number for a given tile, the centers of spheres in the template tile are ranked using dart throwing based technique. To be specific, given the n pre-generated center locations, a random one is chosen at the beginning. Then, a next center is picked such that the distance to the nearest ranked center is maximized. Every time a new center is ranked, the location of the new center as well as the distance to the nearest center are recorded. The ranking process keeps repeating until all centers are ranked. As a result, we have a list of ordered center locations and the maximal bounding sphere radius, which is half of the recorded distance. Apparently, the maximal radius Rk decreases as rank k increases. Using the template tile and the ordered list, we can instantiate the extra tile that is used for modeling non-uniform distributed granular material. Now, let's see how we can instantiate a tile from the template tile. Suppose we want to generate a tile with n grains with bounding radius r. By looking up the ordered list, we keep selecting the grain centers according to their ranks until the corresponding maximal radius Rk is below the specified radius r. All selected centers are intersection-free with the specified radius and serve as candidate center locations for the ring and for the n grains. Then we can pick any subsets containing n elements as the grain center from all the candidates. By randomly selecting subsets for the grain centers, randomness is introduced into the model to reduce the artifact of visible repetitive patterns. Finally, let's look at some results. This one shows validations of our pre-computed GSDFs. On the first row, reference GSDF is computed using Mueller's method, and pre-computation needs to be repeated for different grain optical densities. On the second row, results obtained using our first-order approximation closely match the references, and the same pre-computation can be shared across various grain densities. We provide another set of comparisons to show the effectiveness of our method. This example involves a material of grains with gradually changing colors and densities. A naive solution to approximate the appearance is to discretize the grain optical properties into a number of bins and pre-compute the original GSDF and RT parameters in a per bin basis. However, this leads to noticeable discontinuities. Another baseline is to approximate GSDF for a given density and albedo by interpolating the pre-computed parameters at the discretized grain properties. However, this still yields limited physical accuracy. Relative error with respect to the reference image is shown at the bottom right corner. In comparison, our method offers significantly better accuracy. Next, we show a few examples rendered using our technique. In the first example, we show a pile of more than 100,000 grains with gradually changing colors, which cannot be efficiently handled with previous method. The difference between the reference image and our multi-scale rendering result is subtle in both full view and zoom-in view. the performance increases by 4 times using our framework. The second example is modeled using our tile-based approach, and the scene contains 10 billion screens. Of course, it is not practical to store every grain individually. Our multi-scale rendering results matches the reference closely and is rendered 50 times faster. Also, our tile-based model can support granular material with complex grain distribution. The variation details are obvious in zoom-in views at different locations. For example, the pinkish grain are small and sparsely distributed, while the bluish grain are bigger with denser packing rate. The last example also used our tile-based model, and the thin setting contains 100 billion grains of 2 main types, bright ice blocks and dark space rocks. Again, our multi-scale rendering results enabled by our pre-computation yield significantly better performance. The rich variation in grain properties can be seen from the zoom-in views, which is handled properly with our tile-based model. At the end of my talk, let's look at some limitations of our method. On the rendering side, our method is based on Mueller's proxy path tracing and volumetric path tracing. Therefore, the approximation error brought by the model itself cannot be reduced. Also, our extension cannot handle grain geometry. Removing the dependencies on grain shape by differentiating with respect to the geometry might be a useful extension. On the modeling side, our model cannot achieve high packing rate for non-spherical grains in like rice. In addition, grains described using our tile-based method cannot be easily animated as the grain locations are largely fixed at tile level. An interesting challenge is to generalize the template tile to support animations in a temporally consistent fashion. That's all for my talk today, and thanks for your attention. I'm happy to take any question.
All right, thank you for the nice talk. So let me remind you, please go to Rocket Chat to type in your questions. In the meantime, there's a few thoughts I had when I was watching the talk. So the paper goes into, if I recall, the paper goes into a bit of detail of using a differentiable path tracer. What kind of differentiation is needed? And if I don't have a differentiable path tracer, can I still leverage some of your contributions?
Okay, sure. I think our contribution in the rendering side consists of 2 parts. The first one, we're using a polynomial to represent the parameters used in GSDF and RTE, and that thing is kind of separated from the differential path tracer. So, of course, you can do the interpolation between the densities, so that you don't need any derivative to compute the parameters. Then the part of our techniques, including about the symbolic part, can be used. The differential path tracer is not actually necessary in that case. But of course, in order to have a more accurate approximation, you need more density samples.
Okay, so there's a question from Murat Kurt. Can you model and simulate both homogeneous and heterogeneous materials with your representation?
Yes, I think our method is for both. You mean the tile model?
I would guess so. I assume anything is possible inside of a grain for your method. Is that?
Yes. Yes.
So
yes.
Inside of a grain, you could even have a heterogeneous medium. But I guess
I don't think that's not the case for the for the granular grain. Actually, we assume that the volume inside it is homogeneous. But of course, you can use. No, I don't think our method supports heterogeneous medium inside a grain.
And what about across grains? How do you handle that with the tiles?
Oh, okay. So basically, in our when we render a real thing, we have a fixed different types of grains. By different types, I mean the grain have different shapes and BSDF. But we assume that we allow the volume density and albedo to change within the type. So for each tile, you can specify what types, which percent of the grains are type 1, which percent are grain 2, then for each tile it actually serves as a piecewise representation of the median, so that you can still use the previous proposed techniques to do the approximation in the tile level.
Mm-hmm. So there's another question: is there still random variations of tile-based model in case the point cloud is maximally dense? I guess the spheres, if you use all the packed spheres.
That's a good question. So if the tile is highly packed, then there's actually no randomness. But again, when it's highly packed, because when the actual grain is instantiated, so the pose of the direction, the orientation of the grain is random. So still you cannot see very obvious repetition. But of course, we want to avoid in the case when the radius is very large and meanwhile it's very highly packed, then there might be some problems. So in order to avoid that, you need to choose the number of grains inside the template tile carefully.
So I guess somewhat related to this, I was curious looking at your results, like how, of course, we'd always like to have methods that don't require lots of pre-computation and have the most compact possible pre-computation, allow continuously varying properties. But I'm curious, in the case of granular media, how important are continuous variations? So you had these comparisons to linear interpolation that seemed to work reasonably well, but also granular media in some sense is like a natural diffusion dither. Like if you have a discrete collection of grains, you can perform this dithering across grains, and that also adds extra randomness, like the previous question asked. So did you try just using a fairly coarse tabulation and performing some sort of error diffusion to actually assign one of the pre-computed set of properties as it's varying continuously from some guiding texture? Instead of actually interpolating continuously, you do some sort of quantization and diffusion, error diffusion.
Okay, I think in previous methods, there are different techniques like diffusion approximation or volumetric shared transport. So
I don't mean diffusion in terms of like transport. I mean, if I have a continuous ramp, right, say from black to white, I can approximate that with a discrete number of levels of gray by quantizing deterministically, in which case you get those bands that you saw in your comparison. Or you can randomly quantize so that each grain is randomly assigned in its probability of being snapped to one of these quantized bins depends on the continuous value at that location, right? So if you take an image in Photoshop and convert it to a binary image, you can choose different types of dithering. So you could imagine doing the same thing where each grain in some sense is like a pixel in a quantized image.
Yeah, it's kind of like the result I show in another comparison that we call like linear interpolation. That's kind of similar to what you said. So you have a pre-computation per bin, and then you do kind of interpolation, and then use that as a appearance approximation for the real grain. And then still you can see that the appearance the approximation is still a little bit off comparing to our method. I think I showed that also in the video. And
so in that case, is there less to store for the linear interpolation or more to store? Like what's the comparison in terms of cost? Is it equal time comparison or what's
it's an equal memory comparison. So basically because when we use our method, because we have to consider the number of scatterings inside the grain, then we use the similar memory that is required for the pre-computation and do the comparison there.
So there's a question from Gurpreet Singh. Volumetric attenuation can be non-exponential depending on particle distributions. In your case, does this non-exponential effect, can it be anticipated at the scale depending on what correlations are present within a distribution of grains?
Let me check.
So I think the question is, I guess for the longer range transport, are you explicitly accounting for some sort of non-exponential propagation?
Oh yeah, I think the exponential, I mean, he's referring to the highly scattering grains, I guess. So basically in our experiments, we found that the parameters rather than the throughput, the parameters decays in exponential fashion. So that's why according to our experiment result, we use using an exponential expression to kind of compress all the parameters. That's what we observed in our experiments.
Okay, so I encourage everyone to keep chiming in with their discussion points on Rocket Chat, but due to time, let's leave it at that for now for the live session. This is the last session for today, so I wanted to thank all the authors and especially the organizers for putting on a great show, and I look forward to seeing all of you again tomorrow.